Okay, we're going to look at some sigma notation problems here. Sigma, this is the Greek symbol sigma, spelled sigma. And it's an expression used for determining a sum of a sequence. So this would be the definition of the sequence. And this is the term numbers that we have. We're going from k equals 1 to 7, where you increment by integers. So you're going 1, 2, 3, 4, 5, 6, and stopping at 7. So let's figure out the 7 terms, and then we'll find the sum, and then we'll look at it using the graphing calculator. So our first term is just we plug in 1 for k, so we get 1 plus 1 squared, which is 2 squared, which is equal to 4. Our second term will be 2 plus 1 squared equals 3 squared, which is equal to 9. Our third term is 3 plus 1 squared equals 4 squared, which is 16. And hopefully you see the pattern that we're just dealing with perfect squares, one greater than the term number. So a sub 5 is equal to 6 squared, which is 36. A sub 6 is 7 squared, which is 49. And our last term, because it says stop at 7, is a sub 7 is equal to 8 squared, which is equal to 64. And courtesy of some previous work I've done, you get 203. So let's look at the graphing calculator. There's a sequence function and a sum function. So if we go to second stat and we go over to sequence, and if our sequence is, oops, that's the wrong one. Let's go back. Sorry. If we go to sequence, and if our sequence is defined by let's delete that. Defined by x plus 1 plus 1 squared, comma, delete, comma. So notice, by the way, I changed my mode back into function mode. I don't really need to be in sequence mode anymore. Sequence mode is really only useful when you're doing recursive sequences. So our sequence is x plus 1 quantity squared, and that's just our definition right here, k plus 1 quantity squared. Our variable that we're dealing with in this case is x, so you put an x there, comma, and then this just wants to know what's your beginning input value and what's your last input value. And so there's our values. So if we scroll to the right, we'll see the numbers that we just got, courtesy of doing it without the calculator. So there's also the sum function. So we can do sum, second stat, go to math, down to number 5. We can do the sum of what we just calculated. And there's our sum, 203. So there's sum function and sequence function. So sequence functions really only helpful when you're not dealing with a recursive sequence, which would be an explicit sequence. So this is explicit, meaning that you just plug numbers in and you get values, as opposed to recursive is you need to know previous term numbers to get the next one. So there's one sigma notation problem. Let's look at another one down here. This one's a little uglier because we have some ugly exponents. And we're going from k to n minus 1. So we don't know what the last term is. We just know that we're going to stop at n minus 1. So it's not going to be n terms. There's going to be n minus 1 total terms. So our first term will be equal to negative 1. I plug 1 in where I see k, so 1 plus 1. 2 times 1, so that's negative 1 squared 2, which is equal to 2. A sub 2 is negative 1, 2 plus 1, 2 squared, which is equal to negative 1 to the third times 2 squared, which is negative 4. A sub 3 would be negative 1 to the 3 plus 1, 2 cubed, which is equal to negative 1 to the fourth, 2 cubed, which is equal to 8. And we'll do one more. A sub 4 is negative 1 to the 4 plus 1, 2 to the fourth, which is equal to negative 1 to the fifth, 2 to the fourth, which is negative 16. So our sum can be written out as 2 minus 4 plus 8 minus 16, and obviously the next one would be plus 32 minus 64, all the way out to, I plug in, let's just write out down here, a sub n minus 1 is negative 1 to the n minus 1 plus 1, 2 to the n plus 1. So these two cancel out, so it's negative 1 to the n, 2 to the n, that's 2 to the n minus 1, so that's not a plus 1 right there, that's a minus 1. 2 to the n minus 1. So our last term is negative 1 to the n, 2 to the n minus 1. And that's it.